Somewhere in the darkness between Mars and the asteroid belt, a spacecraft originally built to photograph rust-colored canyons suddenly pivots toward deep space. Its cameras designed to capture the texture of Martian dust storms now lock onto something far stranger, an interloper from another solar system. I'm talking about China's Tianwen-1 orbiter, and what it just witnessed might rewrite our assumptions about visitors from interstellar space. Here's why this matters. When astronomers track objects from Earth, they're essentially trying to see through a thick, turbulent blanket of atmosphere that blurs everything. But Tianwen-1, it's stationed 140 million miles away from our planet, orbiting the red planet with an unobstructed view. No atmospheric distortion, no weather delays, just cold, clear vacuum between the lens and the target. On October 3rd, 2025, at a distance of roughly 18 million miles, Tianwen-1's high-resolution imaging camera, originally calibrated to resolve 2-meter features on Mars, captured something unprecedented. Detailed images of 3IATLAS, the third confirmed visitor from beyond our sun's influence. Let me give you context. Tianwen-1 carries a 38.7 centimeter mirror system that can resolve incredibly fine details when pointed at planetary surfaces. Chinese engineers, recognizing the rare opportunity, reprogrammed the spacecraft targeting algorithms. They transformed a Mars reconnaissance platform into an improvised deep space telescope, tracking an object moving at 36 miles per second relative to the spacecraft itself. This wasn't trivial. The technical challenge. Imagine photographing a rapidly moving pinpoint of light just 3.5 miles wide while your own platform is hurtling through space at 53,000 miles per hour. The solution involved adaptive tracking software that compensated for both the object's motion and the spacecraft's own orbital velocity, capturing 30-second exposures without blur. And what those images reveal demands our attention. Here's where things get interesting. When you look at 3IATLAS through Tianwen-1's lens, you're not seeing a typical comet. You're witnessing an anomaly that sits uncomfortably between categories scientists thought they understood. Rewind to 2017. Humanity detected our first confirmed interstellar visitor, Oumuamua. That cigar-shaped enigma accelerated away from the sun without showing the gas jets typical of comets. Harvard's Loeb sparked intense debate by suggesting it might be an alien solar sail, a hypothesis most astronomers rejected, but which highlighted how little we understood about objects from other star systems. Then came 2I Borisov in 2019. This one behaved exactly as predicted. Ice sublimating into gas, tail streaming away from solar radiation, textbook comet behavior. Scientists breathed a collective sigh of relief. Maybe Oumuamua was just weird, and Borisov represented the norm. Enter 3IATLAS in 2025, and suddenly we're back to being confused. This object was detected on July 1st by Chile's Atlas Sky Survey, designed specifically to find potentially hazardous asteroids. Its trajectory immediately flagged it as interstellar, a hyperbolic orbit carrying excess velocity of 36 miles per second. Meaning it's unbound from our sun's gravity. It originated somewhere near ancient stars clustered toward the galactic center, and it's been drifting between suns for somewhere between 3 and 11 billion years. That timeline is crucial. 3IATLAS may predate our entire solar system, but here's the paradox that's keeping astronomers up at night. Spectroscopic readings show water vapor emissions occurring far beyond the frost line, the boundary where temperatures should lock volatiles into solid ice. Under known physics, this shouldn't be happening. Ice remains frozen until solar radiation heats it sufficiently to sublime. Yet 3IATLAS began outgassing while still in the cold outer reaches where, theoretically, its surface should stay dormant. Some researchers propose exotic internal heat sources. Others suggest unknown chemical compounds reacting to cosmic radiation in ways we haven't documented. And yes, a few bold voices continue asking, could we be looking at something that's not entirely natural? What makes this moment historically significant isn't just the science. It's who's collaborating to figure it out. NASA Solar Dynamics Observatory began cross-referencing ultraviolet data within hours of Tianwen-1's images going public. ESA Solar Orbiter team started refining plasma models. JAXA contributed spectroscopic analysis. Harvard's Hydrocy, specifically designed to investigate unexplained aerial and space phenomena, fed Tianwen-1's imagery into machine learning systems trained to distinguish between natural and potentially artificial objects. Think about the implications. Chinese engineers share raw data through the National Space Science Data Center. American scientists immediately analyze it. European teams model the physics. Japanese researchers add spectroscopic context. All within days, all with a shared goal: understanding this messenger from another stellar neighborhood. This represents a fundamental shift from the space race mentality that defined the 20th century. Remember Apollo-Soyuz in 1975? American astronaut Tom Stafford and Soviet cosmonaut Alexei Leonov shaking hands in orbit above the Elbe River, symbolically echoing where their father's armies met fighting Nazi Germany 3 decades earlier. That mission cost America $250 million and was largely a one-time political gesture during détente. Today's collaboration is different. It's not symbolic diplomacy. It's practical necessity. Interstellar objects don't belong to any nation. They're cosmic libraries carrying information about planetary formation across the galaxy. Studying them requires every telescope we can aim, every dataset we can pool, every perspective we can integrate. China's decision to release Tianwen-1 data openly marks a maturation of scientific culture. Not because of political magnanimity, but because the questions we're asking have become bigger than any single space agency can answer alone. The images, Tianwen-1 transmitted back to Earth, contain a puzzle that challenges our understanding of how matter behaves in the interstellar void. When planetary scientists first analyzed the albedo variations, basically how different parts of the surface reflect light, they found something unexpected. 3IATLAS displays regions of dramatically contrasting brightness. Some areas shine with near metallic reflectivity, bouncing back sunlight like polished glass. Adjacent patches absorb light almost completely, as black as volcanic obsidian. This isn't how ancient space debris should look. Think of it this way: an object wandering between stars for millions of years gets sandblasted by cosmic radiation, micrometeorite impacts, and charged particles. Over time, surfaces tend to homogenize. They develop a uniform, weathered appearance. The moon's regolith is a perfect example. Eons of bombardment created a relatively consistent gray dust layer covering most terrain. 3IATLAS violates that expectation. Its surface appears to be a patchwork of two entirely different materials coexisting side by side. The reflective zone suggests crystalline structures, possibly water, ice, or silicate minerals that maintain geometric order at the molecular level. These materials could only form under specific conditions, either in the presence of liquid water or during slow cooling that allows minerals to arrange themselves into repeating patterns. The dark regions, by contrast, resemble carbon-rich materials similar to carbonaceous chondrite meteorites. These form when organic compounds are exposed to heat and pressure, creating complex carbon-based molecules that absorb most wavelengths of light. Here's the thermodynamic problem. How does an object develop such extreme surface variations while drifting through the near absolute zero temperatures of interstellar space? Dr. Sabina Rai-Dukan at the University of Bern studies asteroid impact physics. When shown Tianwen surface data, she noted something fascinating. The boundary transitions between bright and dark regions suggest rapid thermal cycling, material that melted partially and then cooled suddenly, creating stress fractures similar to cracked safety glass. This implies 3IATLAS' intense heating at some point in its past. But from what's option 1? It originated near a dying star that subjected it to radiation bursts before ejecting it into interstellar space. Quote, option 2, a high-energy collision, perhaps with another interstellar object, delivered enough kinetic energy to melt portions of its surface. Option 3, it contains radioactive isotopes in its interior that generated heat through decay, similar to how Earth's core remains molten. Or option 4, which some researchers hesitate to articulate in peer-reviewed journals. The thermal patterns could indicate artificial materials, composites designed to withstand extreme temperature gradients similar to heat-resistant alloys used in spacecraft construction. I need to be clear here. There's currently no evidence that 3IATLAS is artificial. None. but the thermal history its surface reveals doesn't fit neatly into our models of natural cometary objects. That's not proof of alien engineering. It's proof that our understanding of interstellar matter remains incomplete. Now let's talk about what Tianwen-1 observed around the nucleus itself. The spacecraft's imaging captured something unprecedented, a faint structured halo extending roughly 20,000 miles from 3IATLAS core. At first glance, this might seem like a typical cometary comet, the cloud of gas and dust that forms when solar radiation heats volatile ices. Except this halo doesn't behave like normal cometary outgassing. Conventional comet tails stream away from the sun due to radiation pressure and solar wind. They're asymmetric, pushed outward like cosmic windsocks. But 3IATLAS halo appears rotationally symmetric. It wraps around the object's own axis, forming what researchers describe as a self-stabilizing plasma membrane. This is where magnetohydrodynamics enters the conversation. Let me explain this concept without drowning you in equations. Magnetohydrodynamics, or MHD, studies how magnetic fields interact with electrically conductive fluids, including plasmas, which are ionized gases. When charged particles move through magnetic fields, they generate electrical currents. These currents in turn create their own magnetic fields which affect how the plasma flows. It's a feedback loop. Motion creates magnetism. Magnetism guides motion. In space, we see MHD effects everywhere. Solar flares result from magnetic field lines reconnecting explosively. Earth's magnetosphere channels solar wind particles toward the poles, creating auroras. The sun itself generates its magnetic field through internal MHD dynamo processes. Convecting plasma creates electrical currents that produce magnetic fields, which then influence how that plasma circulates. What Tianwen-1 may have captured at 3IATLAS is a miniature version of this process, a small object generating or maintaining a magnetic field that organizes plasma around it into a stable, rotating shell. Harvard's initial analysis of this phenomenon suggested we might be witnessing rare magnetohydrodynamic coupling in a natural setting, plasma constrained not by external radiation pressure, but by the object's own internal magnetic field. For this to work, 3IATLAS would need to contain conductive materials capable of maintaining magnetic alignment, even in interstellar space. That implies a significant metallic content, possibly an iron-nickel core similar to differentiated asteroids in our own system or exotic minerals with unusual electromagnetic properties. China National Space Administration released a carefully worded statement. Preliminary observations confirm a dynamic ionization structure unlike any known cometary object. Translation: something weird is happening, and we're not entirely sure what. The implications stretch beyond 3IATLAS itself. If small interstellar objects can maintain organized magnetic fields, it suggests mechanisms we haven't fully understood. It means the space between stars might contain structured electromagnetic environments we've been overlooking. It raises questions about how magnetic fields originate, persist, and influence matter over cosmological timescales. And for those inclined towards speculation, stable, self-generated magnetic fields are also characteristics of spacecraft designed to protect themselves from cosmic radiation during long-duration journeys. I'm not saying 3IATLAS is a probe. I'm saying its magnetic behavior is unusual enough to warrant careful investigation without dismissing unconventional explanations prematurely. Tianwen-1's spectroscopic instruments detected something equally intriguing: emission signatures matching hydrated silicates. These are minerals that form only when rocks interact with liquid water over extended periods. Think clay minerals on Earth's surface. Their presence on 3IATLAS suggests this object wasn't always a frozen chunk drifting through the cosmic dark. It likely originated within a planetary system where liquid water existed. More specifically, it may be a fragment from a differentiated body, something large enough that internal heat separated materials by density, creating distinct layers like Earth's iron core, rocky mantle, and crustal surface. The spectroscopic data also revealed traces of iron-nickel compounds, exactly what you'd expect from a metallic planetary core. Here's the picture emerging. 3IATLAS might be wreckage. a piece of something that once resembled a small planet or large moon orbiting another star billions of years ago. Something happened, a catastrophic collision, gravitational ejection during planetary migration, or stellar dynamics during the parent star's death, that tore this fragment loose and hurled it into interstellar space. What we're witnessing now is that ancient fragment slowly disintegrating under solar radiation as it passes through our neighborhood, revealing chemical clues to its birthplace. Every atom currently evaporating from 3IATLAS carries information. Further, information about star systems we can't reach, about planetary formation processes occurring across the galaxy, about the fundamental chemistry that either leads toward life or away from. Let me put this in perspective. We've spent decades launching probes to study our own solar system's formation. Missions to comets like Rosetta Philae, asteroid sample returns like OSIRIS-REx and Hayabusa-2, each costing hundreds of millions of dollars and requiring years of planning. These missions help us understand how our sun's accretion disk condensed into planets 4.6 billion years ago. 3IATLAS just delivered itself to our doorstep, carrying samples from another star's planetary system, and it did so free of charge. The minerals currently vaporizing from its surface tell a story about thermal gradients, water availability, and chemical processes that occurred in an entirely different stellar environment. If we can decipher that story, we're essentially reading the formation history of exoplanets without needing to travel light years to reach them. Here's the profound realization hiding in TN11's spectroscopic data. The chemistry of 3IATLAS looks remarkably familiar. Hydrated silicates? We find those on Mars and asteroids like Ceres, in Earth's clay deposits. Iron-nickel cores? That's the standard architecture of our inner planets and larger asteroids. Volatile ices mixed with rocky material? That's exactly how comets in our Kuiper belt form. What this suggests is extraordinary in its simplicity. Planetary formation follows the same basic recipe throughout the galaxy. Start with a collapsing cloud of gas and dust orbiting a young star. Temperatures near the star remain hot enough to keep volatiles in gaseous form. So planets forming their concentrate rocky and metallic materials. That's how you get terrestrial planets like Earth. Further out, beyond the frost line where water can freeze, you get giant planets that capture hydrogen atmospheres and icy moons. Collisions during this chaotic assembly phase create debris. Some fragments get ejected into interstellar space during close gravitational encounters. These fragments, objects like 3IATLAS, then wander the galaxy for eons, occasionally passing through other planetary. If this process occurs everywhere stars form, then interstellar space should be filled with countless fragments carrying chemical signatures from billions of different planetary construction zones. What does this imply? That the ingredients for planets and potentially life aren't unique to our cosmic neighborhood. The same atomic processes that created Earth's oceans, forged its metallic core, and assembled the complex chemistry that eventually led to biology are operating wherever stars condense from molecular clouds. We're not special, we're just one outcome of a universal process. Now let me shift gears to a less philosophical but equally crucial application: planetary defense. On September 26, 2022, NASA DART spacecraft deliberately crashed into asteroid Dimorphos at 14,000 miles per hour. The kinetic impact successfully altered Dimorphos' orbit around its companion asteroid Didymos by 32 minutes, far exceeding the mission's success threshold. ART proved humanity can deflect an asteroid if needed. But here's the catch. Dimorphos is a rubble pile, a loosely bound collection of rocks held together by weak gravity. The impact created a massive debris cloud, and that ejected material amplified the deflection effect beyond what the spacecraft's momentum alone would have achieved. What if we need to deflect something more solid? Something with structural integrity, like 3IATLAS appears to have. This is where studying interstellar objects becomes a planetary defense priority. Every visitor from beyond our sun gives us data about material compositions, structural properties, and how different types of objects respond to solar radiation. This information directly informs deflection strategies. If we detect an Earth-threatening asteroid decades in advance, the ideal scenario, we can tailor our defense approach based on similar objects we've studied. Rubble piles might respond well to kinetic impact. Solid, monolithic asteroids might require different techniques. Gravity tractors that slowly alter orbits over years, or even nuclear deflection for worst-case scenarios. The more interstellar objects we observe and characterize, the better our cosmic hazard database becomes. 3IATLAS isn't dangerous. Its trajectory bypasses Earth entirely. But it's a free test case teaching us how ancient, differentiated fragments behave when passing through the inner solar system. NASA Near-Earth Object Surveyor, scheduled for launch in the coming years, will dramatically accelerate asteroid detection. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire southern sky every few nights starting in 2025, potentially detecting dozens of interstellar visitors annually. Combine enhanced detection with refined deflection strategies informed by objects like 3IATLAS, and humanity's planetary defense posture improves substantially. I want to step back from the technical details for a moment and talk about what this means, not just for astrophysics, but for how we understand ourselves in the cosmic context. When I initiated Project Galileo at Harvard, my motivation wasn't to prove alien visitation exists. It was to establish that science should investigate any unexplained phenomenon without preconceived dismissals. Whether Oumuamua was a natural iceberg or something else entirely, the scientific method demands we examine evidence objectively. 3IATLAS continues that inquiry. We're not searching for aliens. We're searching for truth about how matter behaves, how planetary systems form, how the galaxy's architecture influences everything from stellar chemistry to the distribution of water-bearing worlds. But embedded in that search is a deeper question. Are we alone? The fact that interstellar objects regularly visit our solar system statistically, hundreds may be present at any given time, most too small or distant to detect, means the galaxy is more interconnected than previous generations imagined. Material from other star systems literally lands on Earth as micrometeorites. Atoms forged in distant suns become part of our ecosystem. We're not isolated. We're participants in a galaxy-wide mixing process that's been operating for billions of years. Here's something I find both humbling and extraordinary. If 3IATLAS proves to be entirely natural, just chemistry and physics doing what they always do, that's actually the more profound revelation. It means the same processes that created life on Earth are operating everywhere. The same chemistry that built amino acids in prebiotic oceans could be occurring on countless worlds orbiting distant stars. The same geological cycles that concentrate minerals, the same atmospheric processes that generate lightning-driven chemistry, the same delivery of water and organic compounds via comet impacts, all of it universal. Earth isn't special except in one crucial sense: we happened here. But the conditions that allowed us to happen aren't unique. They're default outcomes of planetary formation. If that's true, and the evidence keeps pointing that direction, then the Fermi paradox becomes even more puzzling. With trillions of potentially habitable worlds in the galaxy, why is this silence so complete? Where are the others? Maybe technology inevitably self-destructs. Maybe intelligence is far rarer than we assume. Maybe interstellar communication is fundamentally harder than we imagine, and civilizations remain isolated not by physics, but by the sheer scale of space-time. Or maybe, and this is the hopeful interpretation, they're out there similarly examining visitors from other star systems, asking the same questions we're asking, building the same telescopes, sharing the same sense of wonder mixed with existential uncertainty. I need to address the speculation directly. Could 3IATLAS be artificial based on current evidence? There's no reason to think so. The thermal patterns, magnetic behavior, chemical composition all fall within ranges explainable by natural processes. Unusual processes, yes, but not impossible ones. Avi Loeb's hypothesis about Oumuamua being a light sail remains controversial precisely because it requires invoking extraordinary explanations for observations that, while anomalous, don't definitively rule out natural origins. Most astronomers now favor the hydrogen iceberg model. Oumuamua was pure hydrogen ice that sublimated invisibly as it approached the sun, producing thrust without visible outgassing. 3IATLAS doesn't even require such exotic explanations. Its behavior, while fascinating doesn't scream alien engineering the way Oumuamua did to some observers. That said, we must remain intellectually honest. Absence of evidence for artificiality isn't evidence of absence. In journal articles and telescope archives, in refined models of interstellar chemistry and improved planetary defense strategies, in the precedent it's set for international cooperation, the data will persist. That persistence is our answer to cosmic indifference. We can't control the universe, but we can document it, understand it, and use that understanding to better navigate our position within it. So here's where we stand. 3IATLAS approaches perihelion in the coming weeks. Telescopes worldwide are positioned. Researchers are ready. The next phase of observations will either confirm current theories or force us to revise them. Either outcome advances knowledge. I'll be following this closely, as will thousands of professional astronomers and millions of space enthusiasts worldwide. The data will update continuously as new observations arrive. Theories will be tested. Models will be refined. Controversies will emerge and hopefully resolve. This is science in real time. Messy, argumentative, occasionally frustrating, ultimately self-correcting. If you want to follow this unfolding story, subscribe to this channel and turn on notifications. I'll release follow-up videos as significant developments occur, particularly after perihelion, when we'll see whether 3IATLAS survives thermal stress or fragments into revealing peace gauze. Leave a comment below. What do you think this object represents? Ancient planetary debris, exotic cometary material, or something we haven't imagined yet? What questions would you ask if you could send a probe to intercept it? The universe keeps sending us visitors. Sometimes they're mundane. Sometimes they challenge our assumptions. Occasionally, very occasionally, they force us to reconsider what we thought we understood. 3IATLAS is at minimum fascinating. At maximum, it could be transformative. Either way, humanity is watching together across borders and languages, united by curiosity about our cosmic neighborhood. That alone makes this moment worth celebrating.